At the height of 20th century physics, there lived a man whose brilliance was matched only by the sharpness of his judgment. Wolfgang Pauli was revered for his insights and feared for his criticism. When an idea failed to meet his standards, he did not merely call it wrong. He dismissed it as not even wrong. The phrase carried a particular cruelty. It did not mean an idea had failed an experiment. It meant it had failed to even rise to the level where failure was possible. It could not be tested. It could not be falsified. It lived outside the discipline of science itself. That judgment has echoed through physics ever since. Because science is not a museum of eternal truths. It is a graveyard filled with ideas that once felt inevitable. Phlogiston was once taught as confidently as oxygen is today. It explained combustion with elegance and conviction until it explained too much and predicted nothing. The steady-state universe promised cosmic permanence until quasars and the microwave background quietly erased it. These theories were not foolish in their time. They were serious attempts to understand nature. But evidence has a way of outlasting confidence. Eventually, the last believers fade. The filing cabinets close. The idea becomes history. And so we arrive at the present moment carrying a question that feels uncomfortably familiar. Are today's grand theories destined for the same quiet ending? Or are we standing at the edge of something genuinely deeper? Modern physics rests on two pillars that refuse to merge. General relativity describes gravity and the structure of space-time with majestic precision. Quantum mechanics governs the subatomic world with unsettling accuracy. Each works extraordinarily well where it applies. Together they refuse to coexist. Every serious attempt to unite them leads us into territory that is mathematically demanding and experimentally inaccessible. This is where string theory entered the story, not as an answer at first, but as an accident. In the late 1960s, string theory was proposed as a model of the strong nuclear force. It failed. Experiments showed that protons behaved like collections of hard point-like constituents, not soft vibrating strings. By the early 70s, string theory as a theory of the strong force was dead. But something curious remained. The mathematics had produced gravity automatically. A massless spin-2 particle appeared whether theorists wanted it or not. What had failed as a theory of the strong force refused to disappear as a theory of gravity. Over the following decades, string theory transformed from a discarded model into the leading candidate for quantum gravity. It required extra dimensions. It demanded mathematical consistency so strict that only a handful of versions survived. And then came a problem that cut to the heart of its ambition. There was not one string theory, but 5. Each self-consistent, each different, none uniquely selected. At first, this seemed fatal. A fundamental theory should not come in varieties. But in the mid-1990s, a profound shift occurred. What appeared to be multiple theories were revealed as different limits of a deeper structure. What physicists had been studying were not separate worlds, but boundary descriptions of a single underlying framework. That framework came to be called M-theory. M-theory did not replace string theory so much as reframe it. Strings were no longer fundamental. They emerged from higher dimensional objects called branes. These branes could stretch across multiple dimensions. When dimensions curled up small, these branes wrapped around them and appeared as lower dimensional objects. What looked like a string in one description was a membrane in another. The picture was unsettling and elegant. The universe was no longer built from points or lines, but from extended structures whose true nature depended on how closely you looked. This shift carried philosophical weight. It suggested that what we perceive as fundamental may only be fundamental from a certain distance. That depth itself might be relative, but beauty alone does not make physics true. Without experimental access, M-theory risks Pauli's verdict. Not wrong, not even wrong. Then something unexpected happened. In 1997, a new idea emerged that changed how physicists thought about gravity itself. The AD-CFT correspondence proposed that a theory with gravity in higher dimensions could be mathematically equivalent to a theory without gravity in fewer dimensions. Two radically different descriptions. One, underlying reality. Calculations performed in one framework matched calculations in the other, with astonishing precision. This was not philosophical poetry. It was a technical miracle. Equations that should have had nothing to do with each other produced identical results. The correspondence acted like a Rosetta Stone, translating between languages that physics had believed incompatible. Gravity could emerge from non-gravitational physics. Space itself could be encoded on a lower dimensional boundary. For the first time, string theory produced something undeniably solid. Not a prediction about our universe, but a demonstration of internal consistency so deep it could not be accidental. Whatever string theory and M theory ultimately describe, they describe something real in a mathematical sense. The theories are not incoherent. They are not arbitrary. They are tightly constrained structures capable of encoding entire worlds. And this forces a quieter, more difficult question: what do we mean by truth in physics? There is experimental truth. Does a theory describe our universe? And there is structural truth. Does a theory describe a logically consistent possible universe? In the absence of experiments at quantum gravity scales, we are left with the second. This is uncomfortable. Physics was built on the marriage of theory and experiment. Now theory walks alone. Some critics see this as failure. Others see it as a sign that physics has reached a frontier where progress requires patience rather than data. History offers no guarantee. Many mathematically elegant theories have died before, yet few have survived scrutiny the way string theory has. Fewer still have revealed unexpected bridges between gravity, quantum mechanics, and geometry. Perhaps the most unsettling implication is not about extra dimensions or brains. It is about perspective. ADS-CFT suggests that what we experience as volume may be encoded on a surface. That depth may be derivative. That reality admits multiple equally valid descriptions, none of which is privileged. This resonates beyond equations. It suggests humility. The universe may not yield to a single narrative. What feels fundamental may be emergent. What feels incomplete may be a shadow of a deeper coherence we are not yet equipped to see. Whether M theory describes our cosmos remains unknown. It may yet join phlogiston and steady state in the archives. Or it may quietly underpin future discoveries in ways we cannot anticipate. What matters now is not certainty, but honesty. The theory is mathematically alive. Its physical relevance remains an open question. And that openness is not a weakness. It is the space where science breathes. Here at Deep Space Inquiry, we are drawn to these questions not because they promise closure, but because they resist it. The universe has never rewarded arrogance. It rewards careful listening. It rewards patience. It rewards the willingness to accept that our best ideas may be provisional. As we continue to probe inward and outward, we may discover that the final frontier is not a place where questions end, but where our expectations finally soften. Perhaps the deepest truth is this: understanding does not arrive all at once. It approaches slowly from the edges, leaving us changed long before it arrives.